Inside Android SafeTNet Attestation, Attack and Defense, Collin Mulliner. El servicio primario de seguridad en Android hoy en día es SafeTNet Attestation, el cual asegura la integridad de la infraestructura entre la aplicación y el dispositivo del usuario. Lamentablemente, no está bien documentado por Google, por lo que en esta charla veremos dividido en 3 partes cómo funciona, cómo implementarlo en aplicaciones del mundo real y cómo se ataca. Collin Mulliner tiene un doctorado de la Universidad Técnica de Berlín y es investigador de seguridad e ingeniero de software. Pasa la mayor parte de su tiempo trabajando en teléfonos móviles y smartphones. Es también coautor del The Android Hacker's Handbook.
Hello. Thank you for having me. This is a really great conference, and I can finally give my presentation. Okay. More or less all of this was already said. Like, I'm doing mobile phones and mobile phone security for like a really long time. I've worked at like some device manufacturers. I've been on like app security teams, and every once in a while I'll still find device or app bugs and report them to like manufacturers and vendors. And I also have a monthly blog post about everything mobile security, where it's like just like collect everything that's happening and give some commentary or some shameless plug. I was one of the authors of like the Android Hacker's Handbook, and also like recently wrote like a guideline to like do secure app development for like smartphone apps. The one on the left you have to buy, the one on the right is free. So what are the goals for this talk? The main goal is basically understanding what Android SafetyNet Attestation is, and really how to implement it and deploy it like in a safe way. Then, of course, just a deep dive into the attestation itself, and then we're going to look at some attacks and bypasses. And the original idea of this talk was I implemented it, and the documentation was not super good, so like found like small problems here and there, and then completely undocumented stuff, and then suddenly Google added new features, and I was like, this could be better, and I should do a talk about it, and this is this talk. So today, when we talk about mobile apps, we don't really care about apps anymore that don't talk to like the internet, because if it's just like your calculator, there's probably no like security issues. Today is really when apps communicate with some backend infrastructure, then when like security is really important. And of course, like, why is security important? Because there's some service, and if the service like works nicely, the user, so you are like real happy about using that specific thing. And also the service provider, like, they make money and everybody's happy. So if somebody is able to break that, like by either modifying your phone or the app, then everybody's unhappy. And nobody wants to be unhappy. And like app security is really about the app being the gateway to like the service. So there's a lot of modern services where there's maybe not even a website anymore, like Snapchat, for example. But there's like many apps. Like it's a pure app service. So really, the app is like the gatekeeper for the whole user experience. So you want the app to be secure. And also, a lot of applications they manage and display data, like not your data, but other people's data. So in order to make sure that this data is like being handled in the correct way, you need the app to be secure. Otherwise, I can just like say, "Hey, app, give me all the data," and you can like steal it, and you don't want to do that. So like app security is really about protecting the service, the revenue, like the brand, and of course also you, the user. So if you look in generic attacks, what's very common is that people like root their device. And with a rooted device, you basically break all the security assumptions of the platform, because suddenly you can read data from like an app that you should not read. Or you can instrument the app, or you can take screenshots of stuff you shouldn't take a screenshot from. And then there's app modification. It's basically the same thing, but you only attack the app and not the entire platform. And network traffic is kind of a little bit of a solved problem because these days you use TLS and cert pinning. So as long as you can modify the app, it's pretty good. So we're not going to talk about network stuff at all. So a little bit of recap. What is routing? Routing is basically you regain the control over the device, because on a modern device you don't have root, so you cannot like influence or change anything you want. And it's really about regaining access to any resource, being able to read or write any file, and to like modify things. And routing really these days depends on a lot of things, and it's much harder now because of SE/Linux, so basically everything is in the kernel now. So if you look back, how was app security done before, I don't know, maybe like 5 years ago? Basically, you would have static checks in your app, like, hey, is like the SU binary in system XBin, or is like SuperSU, like the SU manager installed, or is Xpost installed, like an app modification framework, or is it, if the app running in an emulator, like is the phone number just 0 and not like an actual like number? Very simple checks, very, very common. That is what like everybody did. But the problem is hard-coded checks, of course. On the one side, for the developer, it's very easy to understand. You're like, if this binary is there, the app doesn't run. Very easy to implement, understand. But for the attacker, of course, like it's very easy to find this part of code, and then you just like patch it, and then you can circumvent the check. So this is really not useful anymore. So modern apps, basically, they collect some information about the app and the phone and do all of the checks on the back end. Because then as an attacker, you cannot just like modify the app, but you have to like kind of know what you can modify and what not. And that's exactly what SafetyNet Attestation will do. A little bit more background on Android. Like over the years, it just became more secure. So you have secure boot, which basically acts as a trust anchor, so you know like your kernel was not tampered with, and then you have a lot of SE/Linux restrictions for better sandboxing. And then Google built this generic platform security service SafetyNet, which has like a bunch of different services. And specifically, like SafetyNet first is really just a brand name for security services on the Android platform. They have a bunch of things like verified apps where you check that's not malware, like a specific thing. So then there's like then there's an API, so an app can install if like malware is installed on the current device. And then there's attestation, and there's like a capture service. And the nice part about SafetyNet, it's really built to be run on any Android device. So it's part of Google Play service, so no matter which Android phone you buy, it is there. So any app really can use it. And yes, the attestation part is about device and app security. So you think, oh, why is Google building that? Don't they control the platform and can make it super secure? Yes, of course, but there's other manufacturers, and their code also runs on like other manufacturers' device. So I guess they wanted like a little bit of an extra service, and they use it, for example, for Android Pay. So if you see like seen a pop-up like this when you try to use Android Pay, that was because SafetyNet thought something was like wrong with your device. Yeah, so they use it a lot. And the nice part, it can be updated without updating the OS. It's a really nice service. So what is actual attestation? So attestation is basically the service where you can find out if your app was modified or the device. So instead of you implementing the SU check, they do that and much more in the background, or like for you. SafetyNet is a piece of code that runs in Google Play service, so in the like App Store app. And even without updating the app, you will always get a newer version of SafetyNet, because it will like, download like this blob of code and just run it. And you basically just call an API from your app and get information about your app and device. So this is just like a screenshot from their original documentation webpage. Like some parts improved over the years, like got a little bit better, but there's like a lot of footnotes and like tiny things you really need to know, which is like not super obvious. Yeah, when I started looking at this, it was different than today. So I don't know all of the difference. So I don't want to say blame them too much for like having bad documentation, but it was definitely not as good as today. This was actually the only piece of code in this entire presentation. So this is basically just like how you call SafetyNet in the application. SafetyNet is part of like the Google API client. So you tell the client you want to talk to the SafetyNet API, and then you just call attest, and then it runs the attestation and gives you back a blob. In this example, I didn't add like the API key. If your app like needs a lot of parallel requests, you need to like get an API key from Google to not get rate limited. Most apps probably don't need that. So okay, how does this actually work? So in the box, that's basically on the device. You have your app, the SafetyNet Attestation service inside Google Play services, Google Play backend, and your own application backend. So you start your app, and your backend says, "Hey, I need to request attestation." And the general code flow is like the backend service will ask its own app, the app will ask the Play service, the attestation service on the device, and that will do something, and then that will call to Google Play services, and then the response will be sent back. Side note, there's like a nonce, which is like a number used once. It's basically to prevent like replays of attestation data. That needs to be incented with. So once your app gets a request and sends a request over to the attestation service, the attestation service does what you used to do. It would inspect the device and also the app that called the service and collect information and send this information back to Google Play, and they run some analysis on it, and then when they determined, is your device good, is the app not modified, they send this response back to SafetyNet on the device, SafetyNet sends it to the app, and your app should send it back to the backend. The response is cryptographically protected, so it's like signed with a Google certificate, because otherwise, of course, somebody in the middle could modify that response. And then on your backend, you validate the attestation. This is a blob. This is the data you get returned. It's basically this like JSON web signature object. It's like 3 base64 encoded things. You have a certificate chain, the attestation data, and the signature. Google has an API to actually validate the signature, but they say it's for development purposes only, and you should implement that yourself. That part is actually pretty solid, so you basically need to do SSL cert validation and check for a specific host name. So the actual attestation data looks like this. It's a JSON blob, and you have the CTS profile match. That's basically, is this device conform to Google's compatibility test suite? Basically means you did not modify the device, or like the device firmware. Then you have the package name, so which app called the attestation. Then you have a digest for the actual APK file. You have your nonce again, and you have the certificate digest. So like the digest of the certificate that signed your app, which should be your own. Google has this like table on what does the different responses mean. The basic message is if CTS is true, your device was not modified. If it's false, something was changed. This extra basic integrity just tells you is your device like rooted or not. And like some apps says like, we don't care if it's not too heavily modified, if it's just rooted. But that's basically, you have to decide what level you want to enforce. But basically, you can just like check CTS, and then you know. So I made this small demo app, which just like shows you some values. You can just like run this app, and then you would see like, hey, my device is CTS compliant, so it's not like not modified, it was not rooted, and the APK digest matches. And I'm going to show a little bit of a demo later about this app and how to have some fun with it. Yeah, so one generic issue is that you're calling multiple APIs and there is networking involved, so errors will happen. And if you don't do like proper error handling, somebody will just like pretend there was an error and bypass your checks. So error handling is pretty important. And unfortunately, the error handling and error cases are not super well documented. For example, they say, hey, if something just didn't work, like the API just ran and you got a positive result, that doesn't mean like that the actually attestation even like ran. And then you get something like that where you just have an internal server error. This basically just means something didn't work, retry. Then you have other interesting error cases where you get a reply that has a negative like CTS profile match. That means like your device was kind of modified, but we also kind of not determine which APK called the API. So you get this like halfway broken and empty JSON result back. And that, yeah, it's where like, it's just like you just have to be prepared for also not even getting APK integrity information. Yeah. And that again is like one part of the whole system that's like a little bit less well documented. So basically, now you know what to do. You can just like add this to your app, and your app's backend will just like tell your app, hey, run this attestation, and then Play service will run the attestation, and then your app backend will know if your device was modified, or your user's device was modified, or your app was modified. But unfortunately, it's like not that easy. As I said before, like there's API calls and a bunch of them and networking. So in practice, like, and if you like implement this like on your personal device and just like play around with it, you'll probably never see any API failure. But if you run it on a lot of devices, you will see API failures, and at every API you call, every intermediate step will fail at some point on a regular basis if you have a lot of devices, and you really have to like have a solution for what you do if like this failure happens. And unfortunately, that's like more or less an app decision. You can, yeah. Then we have other interesting cases where, for example, Play services is too old, and where where SafetyNet is not yet on this device, where you have to like decide, hey, do I force the user to go and like update that specific service on the device? And that's really up to you. In most of the error cases, you really just have to like retry that specific API call and hope that it works. Yeah, and some common failures, like for example, you should not have a too short nonce. It's like very well documented, like at least 16 bytes. Then you can get rate limited, which also should not actually happen. If it happens, yeah, you just add this API key. And then there's just like generic failures, and that will happen all the time. So you just have to be like very aware that errors will happen and you have to retry. And yeah, one idea is basically if everything fails, you report all the different error codes from all the different APIs back to your backend service, because if it's legitimate failures, you can detect that because there's not too many combinations that actually happen. As I said, like if Play service is too old, it will just like your app will just like get 0 output. And for example, on Android 4, you also don't have like secure boot yet. So that's like the next part. We have to like look into. Actually, no, that's a little bit later. So like on different Android versions, you also have different behavior, and I'm going to talk about this a little bit later. Yeah, the final words on API failures. Yeah, you should really start with like just retrying all of the different calls. You can also do an inspection of the attestation. So if you actually get this base64 block back, you can decode it and inspect it. Don't make like your security decision on the device. Just see if you have to like call the API again on the device, because then you save one round trip to the server, and you can just like do the retries on the device until you get something that is useful. Yeah, and as I said, if everything fails, just report the failure codes and make some decisions later. So this basic checks, what most people, I guess, are interested like are the routing checks. But there's more. You can also like actually have your own application check itself, and the check is implemented by reporting digests. So like a SHA-256 of your APK and the certificate that signed your APK back to yourself, and then you can compare that. The nice thing is, the easy mode is, you can, since your app should always be signed with the same certificate, which you need to do, otherwise you cannot update that app through the Play Store, you can just compare the certificate, the signing certificate, and then you know, okay, the app was like not modified. The nice part about that is, if you have 10 apps, you don't have to implement a specific check for every app, because all of your 10 apps should be signed with the same key. It's very easy. And then you have APK integrity. You can also go into advanced mode and use a little bit more of the features, and it's basically, we also check the APK digest. But that means you have to know every single APK you ever released in order to like check the digest of that specific APK. So you have to like be very careful about which version is released like to the public, but you can do cool stuff like you can revoke specific APKs by like digest, by just like saying this is not allowed anymore. But yeah, you have to have like full control over your development, and especially like the release process, in order to use that feature, because otherwise you just like block application versions because you didn't know your developers released them. So some short summary about the implementation part, and then we're going more to like what this thing cannot do. So basically on the client side, you have to like check all the error conditions, report failures to the backend. On the backend, you really have to do signature validation and a validation of this attestation data, and like really check all the fields, like including the timestamp and the nonce, and make a good decision about what you're going to do if, for example, a device doesn't have SafetyNet yet. Are you going to force the user to upgrade like the specific Play Services app? But you will also have devices that are like not modified, but maybe still fail, or fail too much that you might say, oh, this could be problematic. So you want to have like some preparations for that. Like your system should not block them, but have like some maybe whitelisting, some specific, yeah, you have to have like a decision branch that like also like makes that possible. But can we really trust this attestation service? Because when I like saw this and implemented, it's like, oh, this is pretty great. This basically solves like all of the app security problems ever, right? But I was like, oh yeah, there's probably some limitations. Probably people already try to attack it and bypass it. And in general, like probably most of us, when they see like a security system, they really want to like know, hey, how well does it work? Especially if you're like responsible for using like a third-party service to like protect the service or app like of your company. You really want to know like, hey, does this actually like help, or can like anybody who knows like a little bit about Android just like bypass this? So that's basically what I was looking at. The first interesting part is different Android versions. For example, Android 4.5, they don't really detect the boot state. Like they kind of do, but an application cannot vary that information. That basically enables you to just like unlock your bootloader and use like bootloader-based like routing tools, also to like attack like an app, or like root your device with like without maybe being detected by SafetyNet. On Android version 6 and like newer, the boot state and the bootloader lock state is also part of this check. So if you, for example, unlock your bootloader, as I will have on a slide later, your attestation will say like, yeah, that's not really okay. You should like have a locked bootloader, and yeah, it will fail. So it's like also really Android version specific. So if you get information from SafetyNet, you also like kind of want to know which Android version that device is running to have like more information about how trustworthy, the information is. So on Android 4, where you don't have DM Verity is a file system integrity protection mechanism in Android or Linux in general, which basically makes your system partition hard read only, because if you write to it, even if you have root, then the cryptographic check will fail, and the system will like not allow you to like actually run. But like on Android 4, you don't have that yet. So what you can do is basically you root your device and put like your SU binary into like system xbin. And you can just like over ADB get a root shell, temporarily move the files to a different part of the file system, run the app. The app will say, no, I don't see those files, because SafetyNet also just like checks those files in addition to other things, and you bypass it already. Of course, like before you reboot your device, you have to move those binaries back, but there's like already like automation done by people to like manage this kind of things. Yeah, looking at like Android 6, you have this was like a Nexus 5X, and I just like unlocked the bootloader to like check if if this is actually detected. I knew it was, but I wanted to have like make this like screenshot. And you can also see in the bottom on the right, there's like the small advice field, which I'm going to explain a little bit later, but it basically also has a message to the person who reads the attestation, which basically says, hey, you should like lock your bootloader. So it's intended that if an app runs and gets this message, can display it to the user and say, hey, we know something looks wrong with your device and you should like lock your bootloader. If it detects like heavy modification, it would also say like, hey, reflash your device with like an original firmware. So they have like this like advice system also. So some previous attacks on SafetyNet. So in the early, like the Android routing community, as like everybody knows who's like done a little bit with Android and like security, is like really huge. It's like really well organized. And when SafetyNet was first like kind of a thing that like became known to the people who are like active in the routing community, some people started to build basically a mechanism to hide this SU binaries from SafetyNet, just to like bypass the routing checks. And like over the years, this has like really evolved. So like the current best tool is called like Magix, and it's like really involved. You have to unlock your bootloader, patch SLinux policies, and so on. But it's completely automated. You can just like run it, and they even have a test app where you can say like, hey, am I still detected as like non-rooted? Yeah, both information about both. I have a link in the slides, and basically those tools I would call them like it's basically a rootkit. You root your phone and you completely try to hide that from the platform security services. But Google actually plays a really nice cat and mouse game with those people. They would like see what they do and like try to add some detections. So every now and then on those forums you would see, oh, it doesn't work anymore, and then they would like release an update. So there's like this constant improvement, which this is actually pretty good for legitimate like app developers who want to like protect the app with like this service, because Google constantly improves like the security system, where you just like implemented an API call on your app and you just like get constant better security using the system. So that was like the previous work. Those, especially the Magist, is like an ongoing project. The developer behind it seems to be very active, but this really only looks at device integrity. So far, nobody has looked how good is like the app protection, the app integrity protection, and that's what I was looking at. So normally, so like as like the goal of the app protection is that nobody can modify the APK without triggering like SafetyNet, because like if like the digest of your APK changes, you know like somebody modified your APK. And of course, if you could modify the APK, you can just modify the application behavior. Very simple example, you can just like remove like third pinning, and then you can already like tamper with the network traffic of the app, or you can just like patch out other stuff, patch in maybe something to extract data, but you can like whatever you want, you could like implement. So, but how does like the integrity check and how does like all the APK execution and code execution on Android work in general? Because that's going to become like really interesting really fast. So the APK digest is calculated of the APK file that's stored on disk. But Android actually doesn't execute the APK. When you, on older Android versions, if you install the APK, the DEX file inside the APK would just be compiled to like an optimized bytecode, and then the interpreter would like run that ODEX file on as soon as Android switched from Dalvik to ART, the DEX files would be compiled to native code, and the native code would be executed. And like 3-4 years ago, somebody showed like on like I think Android 4 how to like build like a system level rootkit by modifying DEX files, ODEX files. And I thought, okay, we can really use that to attack to also attack SafetyNet. The fun fact, or for me the sad fact, was like I knew that you could like potentially modify ODEX files to get code execution. So I like was tampering with it myself without knowing about this previous work, and then I ran into like one small corner. I was like, just Google that part, and that immediately found me like that slide deck. Like the whole idea of attacking ODEX files is, as far as I know, not super well known. Like not a lot of like people talk about that as like attack vectors. So I think with like SafetyNet it's going to be more interesting. So if you look at how does code run on Android, on like Android 4 and 5, you would have your data and data, your app and data app, and then you have an APK, and then the data from the app would be like under data. On Android 6, you have everything is on data app, and then you have the full package name, and then you have a subdirectory for the APK, you have a subdirectory for the compiled code, yeah, the compiled code is protected by like as a Linux and by the general system security, discretionary access control. So like you don't, not every app can actually read those files. Only like the system server and installed, and of course Zygote can read those files and actually write those files. Even an app itself cannot read its own executable code, which is quite interesting. So how does the general attack work? You actually first you just like download the app from like your phone, and then you modify it. Modification works really easily these days. You have APK tool to unpack and disassemble the code. The APK and DEX files, you just patch the Smalley code. Then you resign the APK, and then you basically have an app that would run. Of course, this APK is now signed with like a different signing key, so you would already fail like the signing key check. But that's okay. So now you take the APK and compile the DEX code to like to ART. Yeah, all of the devices that basically still use ART. So you just like basically run DEX to out, which just converts your APK into an ODEX file, and the ODEX file is then you have an ODEX file that's based on the modified APK. The last step, in order to get this working, you have to patch like the ODEX file. The ODEX file contains a CRC checksum for like the DEX file it was compiled for. If the CRC doesn't check to the DEX file in the APK, the VM, the Android, like the Java runtime, will say, hey, this is probably an older version, we'll just like recompile it and just like delete your modified code again. So you have to modify and patch that out just to trick the VM into not recompiling. That's not a security feature whatsoever, it's just to see like, hey, do we have to recompile? And I made a very small tool which to like just do this patching in a very easy way where you don't have to like think anymore. I'm gonna show it in the demo a little bit later, and it's also gonna be online available. So now you have your modified ODEX file, and how does the attack actually work? Basically, you only need to, like, your goal is you want to overwrite the original ODEX file. So if you have a rooted device, say you have like an Android 4 device, where you have a root that it's not detected, then you can just like go as root and overwrite this ODEX file with your modified version, and then you're good to go. Your win, like your app the modified app will run, and SafetyNet or like other checks will say, yeah, this is like the original APK. If you have a root that it's detected, you can overwrite that file and then just like unroot the device again, and you're fine. Then your attack works. It's pretty straightforward. Yeah, and with that, we bypassed all of the checks because the checks are run on the APK and not on the actual executable code, which I think is a little bit of a design problem. So, but I was like, okay, we now have a goal. We want to basically, this is like my demo app. Now basically my goal was, okay, can I do this attack without rooting my phone? Because rooting like a newer phone is like harder to, like a little bit harder to do. Also, if you want to maybe do like something like a pen test where you say like, okay, like the goal is maybe to like not root the specific phone for like analysis reasons. It would be cool if you like could do that without actually rooting the device, because then you could like patch an individual app, but have like your actual device still be fine. So who else can write this file, or who can write this file in general? It's basically install D, this like package manager, the package installer, and Zygote, like the base VM. But who else could like write the file? Of course, the kernel can write any file, because SE Linux, for example, doesn't count for the kernel. The kernel can do whatever it wants. So last year, there was an interesting bug, the dirty cow bug. I'm not going to talk about any details, but the effect of the bug was you can basically, on a Linux system with like the kernel with that bug, you can overwrite any file on the file system as long as you can open and read the file. Happens that we can actually, as the shell user, you can actually read any like APK, any ODEX file of any application that is installed. So this should actually work, and it actually does. So the attack is completely the same, but instead of like running CP to copy the ODEX file, your modified file over the original file, you just like run dirty cow and use that to like overwrite the file. The interesting part with that is, like, or the small like interesting part with that is, dirty cow doesn't allow you to actually append to a file, so you have to have a file that is the same size or like smaller than the ODEX file. But likely you're gonna like add some code to the APK and like to the ODEX file, so the compiled ODEX file will likely like grow in size, and that's a problem because now you cannot use that attack anymore. But all of the Android devices actually use dex2out and use really heavy like optimizations, like specific processor optimizations. Like here in this example, like my test device, this it's like some random MediaTek chipset based. When the system compiles an ODEX file, it would use like the set instruction variant Cortex A53, and then which will produce like a really big ODEX file, which is like nicely optimized. So the trick really is just like, I was like, okay, what happens if I just like compile it without optimization? Because normally like unoptimized binaries are smaller than like heavily like for speed optimized binaries. And turns out if I just run it without optimization, the file gets much smaller. Even I added code to the original file. It's like, yeah, this is pretty perfect. So that's basically how this works. And I'm gonna like now do a little live demo of this thing. So I'm just gonna install this APK. So it's like when this is installed, you should be able to see it after the camera adjusts to the light. So it's just started, so the light is, there we go. There we go. So it just started, took a few seconds to like run all the checks. And this is like an unmodified device. So this is, yeah, looks pretty good, right? So we're like pretty happy. This looks secure. I'm gonna stop the app. So the binary that we just installed, this is like my self-aware application. So we're gonna we're just gonna just decompile it. This computer is actually pretty fast, so I don't know why it takes so long. We're just gonna open like the main activity file and like the file with some code. So I made this small snippet. We're just gonna send a nice greeting to the audience, if it will work. And then we find the end of the end of this function. You just like paste some code. That's really all you need. Bash. And now we just basically rerun APK, the APK tool, and also resign the binary. Let's say, so now it's just, we have a resigned version. So now, so we have like the modified APK. So what we need to do now is compile the APK to the DEX file. And we just like do this by running this. Basically, it just like pushes the APK to the phone, calls DEX to out, and then downloads the file. So now we have the modified ODEX file. Then we also want to get the original ODEX file since we need that. We need that to like, in order we need to find out like the original CRC checksum so we can patch it. So we have this small little tool to like run it on the original ODEX. So it just shows you the class CRC, that's the CRC from the original file. I just do this. This is like the new one, and then we can now just say, please change this to this. And we can run it again. You see, that's changed. So this now looks to the VM like as it was compiled from the original code. And now we just do and now we just like copy it to the device and overwrite it like on the device. Yeah, so, and now we can go back to this. Wait until the camera catches up with the light. Now we can run it. It says Ekoparty, and all of our nice checks still pass, and me, the poor app creator, is like, oh, everything looks fine, but yeah. And the nice part is like we don't need to like root this device or like any device that still has this bug. So what is like the actual impact of this kind of attack? Of course, it's limited to like any Android device that's still vulnerable to like Dirty Cow, but I think there's like a high number of like those devices still like in the field. The attackers, of course, goes way beyond SafetyNet Attestation because like anything that relies on like the DEX integrity can be attacked with that. Actually, Android 7 devices will be completely fine because the CTS check. So if a manufacturer like wants to get Google's app, they have to run it through an approval process, and the approval process for Android 7 based devices checks specifically for Dirty Cow. So Android 7 devices will not be vulnerable to this. I told Google about this like attack idea like over a year ago. They told me, yeah, they kind of know this attack path exists. One interesting side note, Copperhead OS, which is like a hard and Android clone, they actually automatically mitigate like any kind of these attacks because they're on every restart of an app, they recompile the application, no matter if like the CRC was changed or not, which is like a nice side note. So during the time I was like playing with SafetyNet, I made a number of interesting observations. So the first time I used it, this basic integrity didn't even exist. And like one day I see like this extra field in this JSON blob, and was like, oh, basic integrity, what's that? So I just like tweeted to see, and the only responses I got was either, oh yeah, like a year or half a year later, like, oh yeah, I also saw this, what is this actually? And then a new one, which was added like earlier in this year, like maybe in May, is like this advice field which says like, hey, lock your bootloader or reflash your phone. It's also a new thing. One person from Google actually told me that they also now have like an announcement mailing list. So he said like, oh, if you had subscribed to that list, and I was like, I read your documentation, I didn't really see that list. So they like would announce some of the stuff. But yeah, at that time, like all the other people I knew who worked on SafetyNet didn't know about it. Also, another really interesting part. So SafetyNet can also have like outages, and outages can be like many different things. So as I said before, every device has to run through the CTS test. And the CTS data that is collected during like this like certification process is actually the data that like SafetyNet Attestation relies on. So if you like make say a security update and don't tell Google about the changes you made, then SafetyNet will think, oh, every device that actually had has the security update installed like has like a modified system image. And then SafetyNet will say, no, your device is no good anymore. And that happened to like Yotaphone. I think it's like a Russian company. So like somebody privately reported that like, hey, like this doesn't work anymore. And I was like, and I asked him, what did you do? And I was like, yeah, I installed a security update like yesterday. And I was like, I guess that's it. But also Google broke its own attestation like for their Nexus 6 devices. So they like rolled out a security update, and everybody who installed it, like basically for them SafetyNet was not working anymore. So they rolled back this update, which was like interesting because as a device like as an app, if your job is to protect your app and then you rely on a service and that service breaks, like all of your users will be locked out because you think, hey, they modified their phone. So that's like really something you have to keep in mind when using third-party services. I said that before, like Google is playing a nice cat and mouse game with the routing community. Basically, the routing community now like ensures that Google ups their security, especially like for your app. So that's like a nice side effect. In general, use of this API is free. That also means you don't get any guarantees from Google if like they go down or break something. It's your luck. You're like just out of luck. Yeah. One interesting side thing I thought about was like, hey, so a lot of malware now these days repackages like an Android app. So you take a popular game, add like your malicious functionality, and then you just upload it again to the store. If the people who are doing that are not very smart or very good, and your app is protected by attestation, your app will just like not work, and by that you prevent your app from being used for like malware, which is like a really like nice side effect, which I thought was like worth mentioning. So summary and conclusions. I think SafetyNet is really one of the essential platform security services, besides like the actual like security mechanisms on the device itself. Implementation is a little bit tricky, but it's still relatively easy. And bypasses exist, but it really depends on a number of conditions. In the majority of cases, you will be fine and will be like a great benefit. Especially, you only have to invest time like early on in your app development, and then over time, stuff improves, and you automatically gain those improvements, which is really good. So it's really worth doing, and that's it. Like this one tool to like modify the CRC. That's like there's a link on the first web page, on the first link, and I have a blog, like my daily blog on the second one, where we'll probably write something about it, and slides will be at some point online. And that's it. Thank you very much. This is an awesome conference. Yeah.